Excellent. So, thank you very much, everybody, for being here today in this seminar series of complex systems organized by the group of complex systems at the Universitat Autónoma Metropolitana. For today, we have the honor to have a dear colleague and friend of mine, Damien Challet. So I'm going to spend a couple of minutes to introduce him. Damien did his MA degree in theoretical physics at the Swiss Institute of Technology at Lausanne, Switzerland. Under the thesis, he produced a thesis which is entitled Long-Range Ordering Models of Itinerant Fermions. After that, he did the PhD in theoretical physics at Fribourg University, and then the supervision of Professor Yi-Chen Zhang. And the thesis was entitled Modeling Markers, Dynamics, Minority Gains, and Beyond. After that, he has several positions, starting several postdoctoral fellowships at theoretical physics at Oxford University. Also, at Oxford University, he was in the Mathematical Institute with another position. Then he was also at Oxford Junior Research Fellow at Wadham College from 2003 to 2006. Then he became research scientist at the Institute for Scientific Interchange at Turin. The year after that, for 2 years, he was the group leader in the same institute. He's currently external lecturer at physics department at Fribourg University, Switzerland, external lecturer at HEC Lausanne University. He was associate professor in quantitative finance at applied mathematics at CentraleSupélec, Paris, France. And from 2017, he's a full professor in statistics and data science at that center, okay? He has an impressive CV. He's an expert in applications of physics, or essentially many things in economics or econophysics. I could mention many of his achievements, but I'm not going to do that. I'm going to mention a couple of things which are a bit more personal. He's very fluent. He's fluent in two types of languages: computer languages and human languages, as many of us know. He's fluent in computer languages in C, R, RCPP, Java, Perl, Python, Fortran, and also assembler. He has an extensive knowledge of Unix systems. He even participated in the development of some part of Linux kernel. He speaks French, English, German. He can defend himself in Italian, and he's able to read in Latin and ancient Greek. He has many activities that he enjoys. He plays piano, he skis, he does some fencing, he does mountain biking. And when we were in Oxford together, in a period, he used to love punting, if I recall correctly, right, Damien? And his interests are literature, ballet, opera, history, and art exhibitions. So, and I'm not going to say how old is he, but I was discussing with him the other day. And even though he looks much, much younger than me, and he doesn't want to share the secret of how he looks so young, he's one year older than me, okay? So, Damien, thank you very much for being here with us. Please go ahead with your seminar.
Well, many thanks, Isaac. It's a great honor and great pleasure to talk to you and to give this seminar. Many thanks for the invitation. So I've tried to keep the slides simple. First of all, because I like to keep the slides simple, but also because the format, I think, is more amenable to pictures than long equations. I was a bit blushing when you said all this because I didn't fully recognize myself. But anyway, so today I'm going to talk about something which we don't understand fully, but we know works well. So we don't understand why it works well. But we know it works well, and maybe if I can inspire some of you to try to collaborate on maybe analytical part of this method, that would be wonderful, or even to understand this method. So the point of this method is that in the last, say, 15 years, there has been a lot, very impressive progresses in covariance cleaning, covariance matrix cleaning. And then to my surprise, when we tried something a bit different from what most people were doing, we found something that works better in some cases. So it's something I'm going to show you today. This work has been done in collaboration with Christian Bongiorno, who has just been nominated associate professor at my in my group. So it's a great start for collaboration with him. In the context of portfolio optimization, but in many contexts, if you don't clean the covariance matrix, in some cases that I will discuss today, then if you want to optimize something from unfiltered covariance matrices, then basically you maximize the error. You don't optimize something, you maximize the error. And in the context of portfolio, so in a variance minimization of a weighted sum, basically, Michaud, somebody in finance, coined this kind of, it's not his exact sentence, but it really conveys the idea that you should do something with covariance matrices. So just to fix some notations or some concepts, we have a data matrix R, and generically we have say n objects and T features. Here I will be focusing on time series, but it could be gene expressions in parts of tissues and so on. As you know, if you want to write the correlation matrix in a simple way, you should rescale and center variables so that these R's become X and they have zero average and standard deviation equal to 1. And then you can very simply write the correlation matrix like this. And this gives me the opportunity to introduce the transpose notation, which is here denoted by the dagger sign. And of course, the empirical covariance is well, it can be obtained from the correlation matrix. So in this talk, I will focus more on the correlation part. But if you want, I mean, I will basically switch between the two. But of course, they are linked. So the point is that we know that, well, assuming that the dependence between the features, objects, and so on is Gaussian, then if we know the covariance matrix, we know everything. And we also know that the standard estimator of covariance will be optimal. And if you keep the number of objects constant and you increase, say, the number of features or the number of time steps you have, the length of the time series, then what you know, and which is a good thing, is that the more points you have, the closer you are to the true covariance matrix. That's fine, but in reality, the cost of acquiring this kind of data is proportional to the number of time steps, and basically, you cannot take t going to infinity by keeping n constants. We'll also talk about non-stationary systems. In the case of non-stationary systems, you don't want to have t very large. For example, you don't want to calibrate something in a non-stationary system over t which is much longer than the typical timescale of the say pseudo-stationarity of the system. So there are many reasons why t cannot be as large as you want, and therefore you have to think as t being of the order of n, say 2 times n, 4 times n, and so on. And the problem is, and this is well known by some of you, I know, but the problem is that if you don't have q tending to 0, then you are left with a systematic estimation error of the correlation matrix and therefore of the covariance matrix. And it is well known that what is regular in a kind of perhaps surprising way, what is regular is the noise of the eigenvalues of the correlation matrix. So let me just go through that a little bit carefully. So if all the components of the data matrix are independently identically distributed, and basically I think if they have a finite fourth moment, I think that's the condition. But anyway, what is known is that the correlation of fully uncorrelated independent variables does not converge to the true spectrum. So the true spectrum of a correlation matrix of completely random variables, it's just a Dirac. So all the eigenvalues should be 1 because you have 1 on the diagonal and 0 outside of the diagonal. That's the true correlation matrix. Unfortunately, and this is the Marchenkov-Pastur distribution, that's not the case if you cannot take an infinite number of points. And the beauty of Marchenkov-Pastur distribution is that you can quantify very precisely how much you lose by not being able to take the t to infinity limit. This is well known, and instead of looking at the equation, we're going to look at a picture. So this is a Marchenkov-Pastur distribution. As I told you, the true covariance, the true correlation matrix here is centered on 1 and is a Dirac on 1. It's just a peak on 1. But because you have a finite t, then you have this noise. This is really noise of estimation of eigenvalues of the correlation matrix. You see that the support of this function is finite, so you have a clear minimum value for the smallest eigenvalue and a maximum value for the eigenvalue eigenvalue of this distribution. And this is what I have denoted by lambda plus lambda minus is here. And you see that it can be, well, it depends very simply on Q. And also, so Q, I remind you, is n divided by t. If Q goes to 0, then of course this distribution shrinks like this and becomes just centered on 1, just peaked on 1. It's just a Dirac on 1. And you can also show that, for example, the standard deviation of this distribution, I think, scales like square root of Q. And therefore, clearly, when Q goes to 0, when you have n going to infinity, you don't have any more this problem. But in practice, you do have this problem. And therefore, you have to account for this. But, well, what to do with it is quite simple. So if you measure this kind of distribution, you know that you are being fooled by estimation noise, by the fact that t is not infinite. And here I should insist on the fact that the shape of this distribution only depends on the ratio, on the ratio q, which is n divided by t. So in the limits, the thermodynamic limit, n large, t large, it doesn't, I mean, it's just the aspect ratio of the data matrix which is important, not the exact value. That's quite remarkable. So in any case, for any value of q larger than 0, you have something that looks like this. What you can do is simply to say, well, if I have just something like this, I know I shouldn't get this. I know the true value of that, so I can replace it by the Dirac function. And this is called denoising eigenvalues. It's called noise dressing and so on. But it's really trivial because you know the answer. You know that you have a hypothesis that everything is uncorrelated, so you don't even need to measure the spectrum because you know the true value of the spectrum. Now in practice, and this is the beauty of this picture, which is very old, it's almost 20 years old picture. And at the time, I think these people worked with 24 CD-ROMs, and they had 24 workstations because, of course, a CD-ROM contains much more data than a hard drive. So what you find in reality, for example, if you measure the correlation matrix between price changes, which are called price returns in finance lingo, you find that you have something that really looks like Marchenkov-Pastur distribution, although with some deviations. And then you have values that should not be there if everything were random, fully uncorrelated. So you do have some structure outside of this maximum allowed eigenvalue. And by the way, feel free to interrupt me at any time. So now clearly, if you assume that you have 0 correlation, you expect this. And if you simulate, you really find this. Now what you measure is this. So therefore you have correlations, you have structure, which is very nice. And the point is that to clean that with this idea that this mass of eigenvalues, this dense distribution of eigenvalues here, is just a result of estimation noise. then you would replace this by what you know should be there. That means one peak, right? And it's exactly the idea of generalizing these to more interesting dependent structures, which is this. So in reality, you have a fraction of the eigenvalues which comes from noise, estimation noise, the finite, well, the fact that Q is larger than 0, T doesn't go to infinity, while N is kept constant. And then you have another fraction of eigenvalues which are outside of this thing, which probably comes from noise. And then, so what you do is that you keep those because clearly they do contain some information. You don't want to erase them. And you replace this noisy estimation of a single value by a single value, which is here.
Damien, I have one question,
Yes?
just a clarification. This deviation from arithmetic, I guess, can be due to two reasons, right? One reason is because the data is correlated, or the other reason is finite size effects, right? I guess that what is important, more important for applications in finance is correlation rather than finance, or are both important?
Yes, you're right. What is known here is that this upper limit here is, well, this strict upper limit is only valid for infinite matrices at constant aspect ratios. If you have a finite matrix, then you do have something which is not strictly bounded here, but it does falls off quickly. I forgot how quickly. I think it's something like, it's a power of n, essentially. So these are not finite size effects. These are, if you inspect the largest components of the eigenvectors, you find that, well, the largest eigenvalue is always very, very large, and it comes from basically an average of all the returns. It is called the market mode. It's the index. It's just the average of everything.
Okay. Because sorry, because in another ensemble in random matrix theory, which is the Gaussian ensembles, it is indeed true that actually you have an isolated eigenvalue which is a finite size effect. So I thought that maybe in this case you have, and that weight goes to 0 when you have infinite matrices. So in this case you don't have isolated eigenvalues for finite matrices, right? That's what you're saying.
No, what I'm saying is that these do not come from finite size effects. Okay. They come from the structure of the matrix.
Thank you.
And in particular, and we will see that later today, the US equity, so the stocks, the dynamics of the US market have pretty clear sectors. You will see blocks of correlations that you can attribute to some sectors. And there are other kinds of clustering methods which really find easily sectors in correlation matrices. So really here, in summary, you take this bulk of probably estimation noise of eigenvalues, and you replace them by their true value, which is basically 1 minus alpha here, just to have a to conserve the trace of the correlation matrix. Is just a technical detail. And then you keep those because those are significant. And maybe a few of those here are not significant, but well, what can you do? You still keep them because you don't lose that much, let's say. So this is what is called eigenvalue clipping, and it's one of the first methods to clean eigenvalues, and it is due to Laloux, Potters, Bouchot, and also the group of Stanley in about 2000, year 2000. And if you think about it, what you do here is that you change the eigenvalues, right? You just, well, you modify, you try to clean the noise from the eigenvalues, but I haven't talked about the eigenvectors. You don't touch the eigenvectors. This method belongs in a larger class of covariance matrix cleaning, which are called rotationally invariant estimators, which means you don't touch the eigenvectors because you don't know what kind of structure they should have a priori. So you say, well, I don't know, I keep them. There is another reason is that when you modify the eigenvalues, here, for example, you have 1,000 assets. So you have 1,000 eigenvalues, but then you have order 1 million components of the eigenvectors. So the cleaning of the eigenvectors is way more complicated, complex, and maybe time consuming than the cleaning of the eigenvalues. And this is why people have focused first on the eigenvalues. But then comes a very interesting question. How good can you be if you don't touch the eigenvectors? So if you say, the question is, on average, in a stationary system, how should I modify my eigenvalues so as to minimize, say, the difference between what I find out of sample and in sample? To cut the story short, because, for example, Buhn, Bouchot, and Potters wrote a 120-page review in 2017 and published in Physical Reviews, I think. This has a long story. And all these are optimal, rotationally invariant estimators. They don't touch the eigenvectors. They just modify optimally the eigenvalues. And there are numerical problems to invert some kind of function of some transform, of some mathematical transform. And therefore, some work has been done by Ledoux and Wolf, Barthes, and also the group of Bouchot to invert this. And I think the first paper by Ledoux and Wolf on this is 2012, I think. Just keep in mind this CV, cross-validation or cross-validated way to estimate a kind of spectrum, because you will see this, this abbreviation later today. So this is the best you can do is known. And what is really impressive is that, in fact, I have simplified the notations here, but this in principle must be expressed as a function of what you don't know, of the out-of-sample correlation matrix. And you can show, as Bouchot has shown, that what a given equation, a given way of filtering the eigenvalues is optimal and converges to what you don't know in infinite systems, in infinite matrices. So this is the state of the art. Is really impressive. And even Bouchot has written that it's a miracle, which is not every day that you can read in academic papers. So really impressive work and mathematically really well done. So basically, if you clip the eigenvalues, so this is the unfiltered eigenvalue, the empirical eigenvalue. This is the filtered eigenvalue. And of course, if you don't do anything, you just keep the same eigenvalue, you don't filter, so it's just a y is equal to x line. If you clip the eigenvalues, you transform all the eigenvalues which were smaller than lambda plus, so lambda plus is, so the upper bound of the Martin-Pastor distribution is here, and you attribute the same value to them. And then you keep all the eigenvalues larger than lambda plus. And this is why you have this, it's a step here actually, it should be written as a, the plot is bad, it should be a step here. And just to fix what, I mean, to show you what the optimal way of filtering eigenvalues is nonlinear, and it's basically linear for large eigenvalues, you keep them, and then it's nonlinear for small eigenvalues. But the interesting part here is that you don't have a zero slope. So there is some information in what you don't know about if you only consider Martin-Pastor distribution of fully uncorrelated eigenvalues, fully uncorrelated variables. Another feature which is very important here, so that's, well, all these methods of filtering have a quite specific effect, is that they push very small eigenvalues to much larger values here. And you see this is eigenvalue clipping, which does work up to a point because it has lifted this problem here. This is the famous linear shrinkage by Ledoux and Wolf, which also has this effect. So this is the important point, just for now. The optimal way of filtering eigenvalues is nonlinear and linear for a large eigenvalue, and lifts the smallest eigenvalues. But that's the state of the art. Now, as I told you, to filter eigenvectors is n times more complex than to filter eigenvalues. And there is a way to cheat, which is to take an ansatz. So if you, this is an empirical metric. So we took the correlation of expression intensity of genes in about 320 tissues, so bits of biological tissues in human beings. Um, and if you rearrange the columns correctly, you find this beautiful structure that emerges. And clearly there are parts of or tissues which are highly correlated together and anti-correlated with other parts or other tissues. So you have these kind of sectors, diagonal by block structure. So you do have a structure. So the simplest thing here would be to take a diagonal by block ansatz. So you would say my correlation matrix is, well, you have a blob here, one square of constant correlation. This is a bit more tricky, but this one you would average the correlation here and say, this is a square with constant correlation within this square, and so on and so on. If you look more closely here, you also find a structure within the squares. And this denotes a hierarchical structure. And the hierarchical ansatz, of course, is very old. I mean, every package, statistical package, has a hierarchical clustering algorithm. And therefore, what you could do is to say, well, if you take a hierarchical ansatz, in fact, implicitly, you also take an ansatz for the eigenvectors, because you assume an underlying hierarchical model, stochastic model. To be more precise, there is a very nice method, very intuitive, which is due to Tumminello, I think Lillo and Mantegna, so a while ago. And what they do is basically they do hierarchical clustering, but then they average the intercluster correlations. And because you start from clusters, you grow these squares from the diagonal, then you have these beautiful bands and cleaned versions. So this is the hierarchical clustering average linkage, HCAL, they call it like this way. And you see basically that this whole square or rectangle has been replaced by the average here, by its average, and it's pretty clear. And then it's really, that's the distance, that's the average correlation between this square and this square. And then, of course, because you grow these things from the diagonal, it's less clear. But that's how you do it. The algorithm really here is that you define a distance, which is 1 minus the correlation, and you merge first two objects and then groups of objects according to the pairwise average distance. That means minus correlation between these groups.
And
yes,
Damien, one question. This is very interesting. In this hierarchical average linkage, do you fix the number of blocks in the correlation matrix, or do you optimize it as well? Using
no, you really do the hierarchical clustering, and you keep the tree. You keep the dendrogram of the usual hierarchical clustering, but what you add is that you average you clean the each component of this matrix by taking the inter group at this level, so at each level. But you go for the whole tree, and which is why you have this structure within the structure and so on.
Okay. Yeah,
so that's beautiful. It's really nice, and in fact, it works pretty well for finance as well. Now, if you compare both matrices, it is really impressive. I think this is the clean version of this, and up to a point, it's a good ansatz. Well, up to a point, because if you subtract the original matrix by its filtered matrix, you get this, and things begin to start to be really interesting, because there are still squares, right? And in fact, if you think about it, these squares means that maybe, well, this can be rearranged in a hierarchical way as well, and you will still find another type of hierarchical clustering. So you could filter this with the same method here, and you would get something similar. Which means that there is not a single tree here. So here you have assumed that there is well, I mean, when you do this hierarchical clustering, you assume that there is a single tree, right? And this method respects this structure. It has the same tree, same dendrogram as the usual hierarchical clustering, which is a good feature. But by doing this, it also cannot account for what is outside for all this structure outside of this structure. And in fact, let me go to, yeah, here. So we have taken the same data, and what we did was something a bit bizarre. What we did was to taking bootstraps of the data matrix, and for each bootstrap we cleaned it with this this hierarchical average linkage method. And what we found is that in fact this method essentially hesitates between two trees. And I've tried here to show you a plot of basically you have two bits of the tree, and you find traces of the second tree here. So these are traces of a second possible tree, which is not this one. And so therefore, what we propose here is called we called it BAHC, right? It's for bootstrap hierarchical average linkage. So what we do is that we take the data matrix and we bootstrap it b times. So which means that we bootstrap the lines, right? The time steps, if you like. And to each bootstrap, we apply this method to each bootstrap, and then we just average the cleaned matrices. So there are two possibilities. Either there is really a real simple hierarchical and clear hierarchical structure. So on average, we just get this one, maybe with some fluctuations. Or if the data is very noisy, or if, for example, the hierarchical ansatz is not able to really capture the structure of dependence because the dependence is not a tree, is more complex than a tree. You could have shortcuts and so on, so, or loops or whatever. If it's not a tree, then we will find it as well, because we will have a kind of probabilistic superposition of things described by trees. And in fact, what is interesting is that also this started by the fact that Christian had a paper with Mantegna and other co-workers where they tried to bootstrap the matrix, and they noticed that the structure of the tree was not robust, which could be a problem for detecting statistically validated trees in data, at least in financial data. So what we did was to break that by design and to say we break but we average. And this is the nature of this data. So we have this original, so this is the empirical correlation matrix. We bootstrap the data matrix b times, 3 times here. And then for each correlation matrix, we average it with this very nice HCL method, and then we average. And the point here is that we are able to capture the structure that is not described by a single tree. You can compare with this single tree filtering here. You don't have anything special within these rectangles. But here we do have, you see these blobs here, we do find traces of them, not as strong as here, but we do have traces of that. So therefore, by exploiting the fragility of hierarchical clustering, we are able to describe more. That's the bottom line. So let's see how it does perform in real world. Just a few words. I'm not going to spend too much time on this, but what we are going to do here is that to really judge these methods, we need to have some kind of reference point. If you know the true, well, you can always do synthetic simulations, and you know the true value of the covariance matrix. Then you estimate covariance matrix, and you filter it, and then you try to see which method is the best. Here we are upping the challenge. We say we are going to take a non-stationary system, financial markets, and what we will do is that at each time the true covariance matrix changes, and sometimes it changes very fast. So what we do is that we take the calibration, the covariance matrix in the calibration window, we filter it with different methods, and then we compare it with what happened out of sample. So this means that we should take the number of time steps not too large. There are about 250 days in a trading year. And if you have 500 stocks, like in the S&P 500, in principle, you should take about 5 years of data. But many things do change in 5 years, all the more because the average lifetime of a stock in a stock exchange is about 7 years. And therefore, you would miss a lot. So you take T as small as possible. Right. The good news is that there is a conserved structure between calibration window, in principle and average, between the calibration window in financial markets and the testing window. And you see that these blobs here remain, and therefore we hope to be better than any hierarchical method. Just a few words so that you understand what I'm going to talk about. We are going to try to minimize the variance of a portfolio. What is a portfolio? Well, you invest a fraction WI into each asset. And then you can quickly compute that the risk of your portfolio will be this one. So it's quite easy to show. And then if you want to minimize this risk, according to the covariance matrix that you have measured and possibly filtered, then, well, you have to take the minimum of this. You impose a condition that the sum of weights sum to 1, because otherwise you could just have the trivial solution. And then it's really easy to find via Lagrange multipliers that the optimal solution is this one. The point is that it involves the inverse of a covariance matrix, which is problematic, as we have seen, if n is roughly equal to t. Or even if n is larger than t, so if you have more objects than time steps, then in principle you cannot do this. Quickly speaking, whatever you think you will have in sample will be wrong out of sample, because so you optimize your weights in the calibration window according to the possibly filtered covariance matrix, and then in the testing window, the out of sample window, you still have the weights which are optimal for the in sample covariance matrix, but they reapply to the out of sample covariance matrix. So of course it cannot be the same one, and therefore you always overestimate your ability to optimize noise. What is really nice, there is a very nice result by Pavka and Condor, is that if you really have zero correlation in your data, then the expectation of the ratio of the error diverges when t reaches n. So if you start with, say, 2 times n and you decrease t, then what you get out of sample has nothing to do with what you get in sample. Right, so what is really nice is that when you bootstrap the data and you compute the average correlation matrix, even in unfiltered, on the bootstrap data, then you don't have anymore the problem of zero eigenvalues of the correlation matrix. And in fact, it is relatively simple to show it. And Christian has written a paper about this, which should come out this year. And therefore, because we use bootstrap, we also lift the problem of not being able to invert the covariance matrix for, say, I don't know, you have 500 stocks and we can take 50 points, 50 time steps, which is, I think, great. And actually, it does work well. And there are several ways to compare how each method works. I mean, how well it works. The first thing that you can try to see is whether the eigenvalues are close enough on average. So what we do is that we have a large data set, 20 years, 1,000 US equities. What we do is that we take random subsets of assets, 100 assets, and on random periods, and we do this 10,000 times. And we compute the in-sample covariance matrix or correlation matrix. We filter it with different methods, and we compute the distance between the calibration filtered eigenvalues or eigenvectors and the out-of-sample ones. To compare the eigenvalues is not that simple. We could use the log, but here we have used, for example, 2 measures. One, which is simply the average difference between the ranked eigenvalues. And we see that if you don't filter anything as expected, it's bad. This is the empirical the results for the empirical correlation matrix. And this is the result for CV. So CV is one of these optimal rotationally invariant estimators, and you do expect that they filter the best, the eigenvectors values, sorry, because they are precisely made to filter optimally and provably optimally eigenvalues. But we are here, right? So it's not too bad. So this was for the large eigenvalues. Now for the small eigenvalues, which in fact matter most for portfolio optimization, because when you take the inverse of the covariance matrix, you see that BAHC is the second with respect to CV, so to the optimal rotational invariant estimator. So we also do not too bad. We're not as good as the optimal eigenvalue cleaning, but we are not too bad. So if now you do the same thing, but for the eigenvectors, this is where things start to be very interesting. We do much better, right? This is for HCAL, so the without bootstraps, this average, this hierarchical average linkage clustering. So without bootstraps, and you see that with bootstraps, we are able to describe better the eigenvectors, and therefore we do extract more information with these bootstraps, and we are basically always better. So here you have 100 assets, and here T-in is the number of time steps in the calibration window. And therefore you see that we also do well, even for very small T. So even for T smaller than N, we do well. If you have better eigenvectors while having not too bad eigenvalues, what you hope is that when you apply this to portfolio optimization, and maybe I should point out here that portfolio, well, mean variance or global minimum variance optimization is applied, for example, in investing, but it could be in investing in wind farms, for example. If you want to know how many windmills to, well, I mean, how many, well, the size of each wind farm in each location, depending on the wind speed correlation between all the sites, for example. These are methods which are used to compute this. So it is here applied to finance, but it's more generic than this. Anyway, so we do well for eigenvectors, and we do not too badly for eigenvalues. So our hope is that we do well as well for portfolio optimization, and that's the case. So here, this is the usual. But this is the optimization I have shown you before. So that you try to minimize the variance, having the sum of the weights equal to 1. And it is well known that if you don't filter the covariance matrix, you get this absolutely horrific out of sample performance. This is the empirical one, unfiltered one. And this is the linear shrinkage, the old linear shrinkage of Ledoux and Wolf. And you see CV and Quest are basically the same thing at the end. There are two algorithms of rotational invariant estimators, but they do the same thing, and they are not so good for in the very high dimensional regime where you have less data points than objects. And basically BAHC is the best one. So you can really put, I don't know, T is equal to half N, and it still works well. Long only means that you add an additional constraint. It means that you can only buy something, not sell. Take a short position, that means you sell the assets without owning it beforehand. We are also quite good, and even the best by far, even if T is larger than N, so you are not in the high dimensional regime, but we do really well, basically. But we are not happy. This is the probability that we do better than any methods. It does work well. Now, we're not happy because we have filtered the correlation matrix with this BAHC method. So what we can do is that we can apply the BAHC method to the residues. So you apply the BAHC method to these residues, and remember, it's not exactly the same picture, but here this is an example of residues here. So you apply the same method to this, and it should contain some structure. And you try to squeeze out more information from the residues. And therefore you can define back applied twice, so the correlation matrix with back applied twice, and you define it in this way, and then you can iterate and do it k times, and this is called k back. What is very nice is that you have much better eigenvectors because you can extract more structure from the correlation matrix. But in fact, we have a problem right now is that we have worse eigenvalues. You see, this is the best way to clean eigenvalues, and back alone done once is pretty good. And then this is when you apply it if you apply 5 times back and 15 times back, you see that there is a bias that comes. But nevertheless, we can try to run the same thing again. And in fact, if you apply back more times, it's even better than before. So this was back before. So when applying back once is worse when t is very large compared to n, is worse than other methods. And of course is worse than for example CV, because CV is clearly optimal. Is designed to be optimal in this region. However, if you increase the recursion level, you see that you can even increase further the performance of this algorithm. And the point is that we don't understand fully why, and there are no analytical results, for example.
So Damien, one question, because this is very interesting. In this plot here, you are showing just the different, so the different 1, 3, and 5, this is a k-back method for the different case, right?
Yep, yes, that's right.
And I see. And you say that when you increase you apply a back method to the residuals, for some reason, you get worse estimation for the eigenvalues when you increase. Do you have some idea why? That's strange. So it seems like there is a trade-off that you can have, you know, at the same time, good eigenvalues and good eigenvectors. Either you have one or the other, but you cannot have both.
Yes. If you apply the methods exactly like we have this defined and published, you find this. So we are working on this, and
okay. We
can improve further. Yes, absolutely.
Okay.
I'm almost finished. Yeah, this is just because this is by having these random assets and random periods just to know unconditionally if we do better or not. And this is if you take the full universe and you try to apply different methods, just to give you an idea of how you can, how you really obtain something that is not much volatile. So we optimize here the out of sample variance, and you see how little the variance is. We don't at all optimize the return, so the slope of this. But since on average things go up, then it goes up. That's why it goes up. And we did include March 2020. This is when we wrote the paper. Everything collapsed, but as you know, then it went back up. So I'm finished. We have written a package for Python and a package for R, which are available on PyPy and CRAN. So you can try it yourself. It's very easy. There is one function, which is filter covariance. And there are two functions. There is one which is filter covariance, another one which is filter correlation, and that's it. And you can modify K if you like. So what needs to be done is exactly your question, Isaac, is can we have both? Either you improve the eigenvectors of back, but I think K back is good for that, or you improve the eigenvalues of K back. We are working on this, and I think we will manage. What is more puzzling is why it works at all, and we don't know the limit of validity of this. We don't know, for example. We don't know. We don't have a criterion a priori. If we are given one correlation matrix, we don't know if back or K back would be better than another method. What we do know is that it does work well for very small, large Q. Sorry, and if you look at many estimation methods in statistics or elsewhere, you find everywhere that the inverse of the covariance must be computed. So we are trying to generalize and to see if it can be applied in other domains. So you should have roughly a hierarchical structure, but a more complex than simply a hierarchical structure. So these are the things we should like to work on in the future. Well, thank you for your attention.
Okay, Damien, thank you very much for this very interesting talk. I have many questions, but before I question you about many ideas I have, or you know, maybe some things you have working right now. Maybe some of the colleagues, do you have some questions for Damien? Please go ahead. There are two ways to ask. Okay, just simply unmute your microphones and ask directly to Damien, or either if for some reason you have some technical problem, just write on the chat and I can read the question to Damien. Please go ahead. So Damien, we have many students here. Some of the students are my students, and they tend to be very shy. Okay, so let me ask a couple of questions while the colleagues think about other questions. Like the first one is, I remember actually that Jean-Philippe, I was in Les Souches in 2017 in a workshop. I'm not sure whether you were there. It was about the stochastic processes and things like this. And actually Jean-Philippe introduced this thing of rotational invariant estimators, which has more or less the data where they were working on this, okay? And you know, analytical, you can do many things. For covariant matrices, there was an open question of what happens with, I think the name was cross-correlation matrices, when you have different time series so that the covariance matrix is not symmetric. So can you tell us whether that type of covariance matrix is important in a portfolio optimization or maybe in other areas, and whether your method could be applied in that case as well?
I have no idea. To be honest, I don't know at all. Maybe we should look into that. But it's not something we have investigated yet.
Okay. Another one is that what are you, point three, what are you trying to do analytically without revealing, of course, your secrets, okay? Because again, for rotational invariant estimators, so you have the power of a random matrix theory where, you know, for Marchekov's theory, you know many things. Maybe for certain calculations, you have to, that appears in the paper of Bouchot and collaborators, you have to get you have to use many different, you have to apply many different techniques from free probability theory, etc. Okay, in your case, what are you, which techniques, methods are you trying to use to get some analytical results out of this, to understand what's going on?
That's the point. We don't know.
That's the point. Okay.
Yes. No. Clearly, if you assume that you have, on the whole, certain candidates hierarchical models, then you would have some kind of mixture of hierarchical models, and then you would. I would expect that if you can derive, well, I mean, the first result you could derive would be to assume a mixture of hierarchical models, then to generate, well, and then to try to do inference with these things and to see the limits of resolution and so on and so on. But things are really complicated by the fact that you have bootstraps.
Mm-hmm. And for domains of applications, what are you thinking about outside finance and portfolio optimization? Just that some of the students here can have a look at different domains of applicability.
Well, there are, I mean, this question is well, has two aspects. So the first one is from a statistical point of view, from a methodological point of view, where do you use a covariance matrix in inference? And so is it better? I mean, is the method better if you use this, if you use BAHC or KBAHC than anything else? And by the way, now I see that Ledoux and Wolf precisely do this. They revisit statistical methods, and they apply nonlinear shrinkage as well as the statistical method, and it does work really well. So what we do is that we apply BAHC instead of nonlinear shrinkage, and we try if it's better. So this is really from a methodological point of view. The other question is, in which domain are things roughly hierarchical? So you have seen that for this gene expression data sets, things were clearly interesting. And if you talk to biologists, they say, yes, we use these hierarchical ansatz because it gives us a first clues about the separation of objects. So they use this for that. But then we don't know what it would mean to them. What the fact that you would have several trees, for example, would mean to them. If would be, if it's important or not.
I see.
It's really about the nature of the data they have.
Sure.
For example, we know that the US stock market has this beautiful structure, but if you try, for example, the Hong Kong Stock Exchange, it has less of this structure. Mm-hmm. BAHC is still very good, but you find, the pictures of the covariance matrices are less impressive. This is why I presume many people use the US stock market.
Mm-hmm. I see. Very good. Any other questions, colleagues? Well, if not, Damien, thank you very much for again to give the seminar. It was a long overdue, okay, to meet,
yes, it was
virtually in Mexico City.
Yes.
But thank you very much for being here. So, colleagues, shall we unmute the microphones and just thank Damien for this fantastic talk. Thank you very much, Damien.
Thank you, everyone. Many thanks.
Excellent. So next week, we continue with the series of seminars. We have a postdoc student from the group of Lenka. He will talk about machine learning, deep learning, and things like that. Thank you very much, guys. See you next week again. Damien, thank you very much. Bye-bye.
Bye-bye.